So good morning, everyone. Good morning on the day four. Very warm welcome to all of you for the 5 days training program towards carbon neutrality in construction strategies and solutions. Today we have our guest speaker for the seventh session. Allow me to welcome Professor K.D. Atia, a global recognized leader in sustainable architecture, building technology, and the head of Sustainable Building Design Lab at University de Belgium. With dual Belgian and Egyptian citizenship, Professor Atia brings a unique perspective shaped by his international education and experience. He holds a PhD in sustainable architecture from the University Catholique de Louvain, Belgium, and has pursued advanced studies at Texas A&M University, USA, and Wageningen University, the Netherlands. Over the course of his illustrious career, he has contributed significantly to the fields of net zero energy design, building performance simulations, and climate resilient architecture. With an impressive H index of 43 and 3,500 plus citations, uh, Atia has led groundbreaking research projects such as Dynamic Renovate and Renovation Platform with focus on decarbonization residential buildings and developed data-driven renovation tools. His work on tall timber buildings and overheating indicators reflect his commitment to address emerging challenges in the sustainable construction. As a complete author and editor, Professor Appiah's publication include a widely cited book, Net Zero Energy Buildings, Concepts, Framework, and Roadmap. He is also a leading educator, having designed and taught new courses on building technology and structural design. We are privileged to have you, sir, and we are very thankful to share your expertise with us today. Please, sir, over to you. And, I hope all the participants are active now and hope all of you have a great session now. Over to you, sir.
Today's presentation, I selected the title Pathways and Solutions Towards Net Zero Whole Life Carbon Buildings by 2050, and allow me to open a window for you about what we are doing in Europe. Maybe some of you will criticize some aspects. This is completely acceptable, but allow me in the same time to give you an overview of what's happening in Europe. This is what the European 27 member states are thinking about, concerned about. For sure, the two key problems, from one side, we are trying to mitigate the climate change consequences related to the overheating and discomfort problem. But from the other side, we are trying also to solve the root cause problems. So this presentation is more about the root cause problem. What is the root cause problem? Today, the root cause problem of climate change is the emissions. So in this context, I'm honored to be invited by this program or this week, and I'm going to share with you some insights. First of all, I want to acknowledge Professor Dr. Chandra Shekhar, who invited me for this training. Before starting, I would like to inform you that the presentation is part of a larger consortium, which is the Global Consensus on Sustainability in the Built Environment. And in this consensus, we are looking to investigate all the potential of reduction of carbon emissions related to the construction sector, whether it's on the architectural level, on the construction level, or on the engineering level. And also, this presentation is part of the Path to Zero Carbon Challenge, which is in the United States. And for sure, the work that I'm going to share with you is part of a collective effort within the International Energy Agency Annex 89 on pathways towards whole zero carbon buildings. Well, just to give you a heads up, what are we going to face or the structure of the presentation today? I'm going to talk about the causes of climate change, the why whole life carbon buildings are important, and why we are switching from energy to carbon in the calculation approach for standards and building codes. What is net zero whole life carbon building today? How to define such a building? How to quantify its performance? What are the pathways and solutions from an architectural and technological approach to reach those types of buildings, and some concluding words. And during the presentation, for sure, I will have some short interactive quizzes. So let's start with the cause of climate change. It's very important that we get closer to climate scientists and try to understand how they see the problem of climate change, because at the end, we are professionals, we are building professionals, we are designers. Sometimes we are not so aware about how we can reach this and what are the causes of climate change. Here, this is a little example of a climate disruption. Maybe not many people were talking about it. It happened in North Africa, in Libya. And these type of floodings are now occurring all over worldwide. We just had 1 month ago a very similar flood that was in Valencia, in Spain. So maybe I'm sure that also in Asia there is different types of floodings like that, that you can see the whole city is wiped out. And what happens actually, in fact, that we find a series of rain and storm rains that occur with long distance on long-term duration, 3 or 2 days, and suddenly we find a huge amount of water that floods complete regions and urban agglomerations. So what we are going to face in the coming years until at least 2050, if we do not reduce the emissions of the planet and cool down the planet fast, we'll have a lot of climate disruptions: floods, sea level rise, windstorms, heat waves, fires, power outages, earthquakes, water shortages, air pollution, pandemics. And every country, every region can list its own extreme events depending on the local climate conditions. So you are familiar with these kind of disruptions that will continue. They will get more intensified. They will get more magnified. So it's important to be aware about it. Well, if we look to the most recent agreement that had a kind of consensus worldwide, it was the Paris Agreement in 2015. And during that event, the different countries agreed to keep the temperature under 1 degree Celsius. And the purpose here is to maintain this increase of temperature as 1 degree Celsius. One would say, what is 1 degree Celsius? It doesn't make sense. Actually, 1 degree Celsius is just an average for the whole planet. So in some areas, the 1 degree Celsius could be 10 degrees difference, minus or positive. And imagine that in your region or in your city, you have an increase of 3 degrees or 5 degrees. Sometimes in Indian cities, we can have a difference up to 8 or 10 degrees. This will make a significant change and will impact the whole building eco-services and all living aspects related to the quality of life. So it's very important that we try to keep this, maintain this limit of +1. Unfortunately, we exceeded this limit or this threshold of keeping the temperature increase of the planet by an average under the +1 degree, and we are now around 1.6, 1.56, something like that. Unfortunately, if we will head towards +2, which we are going to, and unfortunately this year was a very high emissions year economically, we are unable to slow down the use of coal and all the petrochemicals. And unfortunately, this means that we are heading towards +2. +2 means that we are going towards a catastrophic scenario where we will have areas in the planet that could not be livable. So it's very important to come back to this agreement and try to monitor the increase of temperature worldwide as an average value and keep it under at least the 1.5 threshold. And the only way to do that is by reducing the emissions and reversing the heating risk. Now, when we look at the carbon neutrality and carbon neutral community, they are self-speaking. It's a very logical approach in order to make sure that our footprint and our built environment has a neutral carbon impact. And in order to do that, we can see that there's a distribution already of zero energy buildings worldwide. We can find them more concentrated in Western countries, mainly Europe, United States. We find some representations also in India, Southeast Asia, especially Korea or Japan, the east coast of China, and some also projects in Australia. But what is the most important point here to take into account is that historically we have been working with the net zero energy paradigm, which is very simple, that we have buildings that are ultra efficient, very energy efficient buildings, well insulated, with proper glazing, with proper ventilation and passive cooling technologies based on the bioclimatic principles. And at the same time, they have building integrated renewable systems such as photovoltaics, for example, that produce the energy consumed over a year. So you can see that in the core of this zero energy communities, we will have two aspects that are very important: storage and scaling up. And you can see if we are going towards carbon neutral communities and we want to increase these types of constructions, we need to make sure that we already have standardized the net zero energy buildings way of design and construction and operation, and that we have already neutralized the carbon, the mobility sector, or the car, we would use also carbon neutral vehicles, and with that we have also smart grids that are decarbonized, meaning that we have grids that can interact with buildings, we can export or import energy, and at the same time these carbon grids are in a way or another decarbonized as much as possible, so that we reduce the reliance on coal or any high emitting sources of energy and emissions. And definitely the connection between all three aspects here will be storage. So in the future, storage will be the key in order to succeed this transition towards carbon neutral communities. Now, what are the causes of climate change if we are going to check it from a pure physical point of view? Well, as you know, the Earth is exposed to the sun, and the sun is transmitting visible radiation, and is also transmitting infrared radiation. Historically, we had this reflected sun, which include the reflected infrared. This reflection was in itself a cooling aspect or a way to cool the planet. However, what happened with time, with the release of greenhouse gas emission gases, which are results of the industrialization process and modern lifestyle, we created a layer in the atmosphere, which you can see in this green color. This layer is kind of isolating layer that does not allow the direct radiation to just reflect back in the open atmosphere, and this means that the heat or the infrared stays trapped. So it's partially absorbed, and it stays a long time in the atmosphere layer, meaning that it keeps being re-emitted and re-emitted, and this situation causes the overheating of the atmosphere layer that borders the planet. So actually this is the main cause of climate change. Now, if we go further into detail, what are the reasons of the creation of this green, let's say, layer that is blocking the solar reflection? If we look at the release of gases, actually we are burning fossil fuels such as coal, oil, natural gas, and all the deforestation activities, resulting that we are releasing a lot of carbon. What happens that this carbon aligns with oxygen molecules, resulting in the creation of a new composition, which is the carbon dioxide. The problem with this carbon dioxide that it stores the heat, and it does not allow to the reflection of solar radiation to the outer bounds of the atmosphere. The second thing that we are doing in our economical and social life, we are releasing through the livestock methane, through the agricultural practices, the decay of organic waste and municipal solid waste, for example, the landfills, and so on, next to the process of coal, oil, and natural gas burning, which results that we also release carbon that aligns with hydrogen, resulting into the creation of methane gases. So these two gases, the carbon dioxide and the methane together, they block the atmosphere, or kind of they dominate the gases in the atmosphere, resulting that the heat gets trapped in the atmosphere, and resulting that the reflection of the direct sun radiation gets trapped, as we mentioned in this phenomenon. Now, when we look at the gases and their impact from climate change and how they causes climate change, we can see that the very dangerous gases are the carbon dioxide, the methane, the nitrogen oxide, and you can see also all the hydrochlorofluorocarbons, for example, or the chlorofluorocarbons. Those are gases that are mainly used in the refrigeration industry. All this group of chlorofluorocarbons are used in the refrigeration industry. As I mentioned, the CO2 is a result of burning fuel and petrol, and then the CH4 and the nitrogen oxide, they are resulting of methane and agricultural activities and landfilling. If we look on the right side on the emissions level or the factor of presence of these gases in the atmosphere, you figure out that their presence is very high, and they can, in particle matter, in a very small unit, ppm, they are highly represented in the atmosphere layer. So what we are trying to do is that we are trying to phase out and reduce these type of gases in order to make sure that the atmosphere layer is not blocking the reflective side and the infrared radiation coming from the sun. Moving on with the presentation here, I want to have some interaction with you. So maybe if you scan this code, and I have a little question for you. Maybe we can start to have your opinion. Are you ready? Just if you have your smartphone, can you scan this code? From my side, I will try to give you 1 minute, and then I will show you open the results. So the answer of the question is simply, the correct answer is, as you can see, it's the fluorinated gases, followed by carbon dioxide. Then we have methane and nitrous oxide. This is the order of the gases that causes the climate change. Now let's move to the following point. You can see here that the consequences of climate change is that we are now also moving from using the classical indicator of energy use intensity. In the past, we were using energy use intensity in kilowatt meter squared per year. So historically, we were using that as the universal indicator to quantify the energy use intensity of building. Today, we are abandoning this indicator, and we are stopping to use this indicator of energy use intensity of buildings, and we are using another indicator, which is mainly the green warming potential, represented in kilogram CO2 equivalent per square meter per year. So today, in order to assess and evaluate the performance of a building and claim that that building is sustainable or green or energy efficient or carbon neutral, we need to quantify the emissions of these buildings in kilogram CO2 per square meter per year. And what is here very important to take into account, the term equivalent. Actually, why we are saying equivalent? Because like I mentioned earlier, we are not only taking into account actually the carbon dioxide, but we are taking into account the agglomerated weight of the four gases, which is the fluorines and the methane, nitrous oxide, dioxide, and carbon dioxide. So this is very important to take into account. And as you can see, the share of these gases are very significant. For example, if we are talking about hydrofluorocarbon 134, this is a gas that is released based on the use of refrigerants. You find it in your fridges, in the air conditioning units. This has an equivalent of 1 molecule of this HFC 134 has an equivalent of 1,000 molecule of CO2. Same story here. The equivalent of nitrous dioxide has an equivalent of 310 of carbon dioxide molecules. 1 molecule of methane has an equivalent of 21 molecules of CO2. So actually, what we are doing today is that we are quantifying the release of those 4 gases associated with the construction and operation of buildings, and we are using an equivalent functional unit, which is greenhouse gas emission equivalent in kilogram per square meter of built up area annually, to quantify the representation of these gases emitted during the construction or operation of building. So this is very important to take into account, because this will be the most important indicator that's going to be used in the coming years. Now, how are we going to calculate such emissions? Well, what we are doing today in our practice is that we are using the term net or zero net carbon buildings, and we are measuring the energy consumption associated with lighting, equipment, cooling, pumps, fans, heating, and hot water for building during their life. And what we're doing here is that we transform this energy, divide this quantity of energy on the gross building area, so to get a unit per square meter. And then instead of calculating the total energy use intensity, we are transforming it directly to greenhouse gas emissions. For sure, if we have any renewables that are on-site or off-site connected to the building, we will extract them from our emissions calculations. And finally, we are getting to the final emission through this simple equation. Definitely, the energy mix plays a role, because if we are grid connected, depending on the grid emission intensity, if my grid is fully relying on carbon, on coal, for example, I will have a high emission factor. If my grid is relying on renewables or nuclear, I will have a low emission factor. And by that, we can estimate on an annual basis the emissions related to the energy operation. So from this equation, we are today defining the zero net carbon buildings definition, and we are able to share this information. And ISO 52000 is giving further details if you are interested in the calculation approach. Now, what we are also using in the indicators today, because we are living in a climate or in a planet that is heating up, we are using the second most important indicator, which is the indoor overheating. Indoor overheating, we developed in our lab a complex indicator that is based on 4 metrics. This overheating indicator is very important because there is no meaning to communicate the emissions intensity of a building without communicating the comfort conditions. The buildings, is it providing comfort? Is it how many are the discomfort hours? What is the situation of overheating? So with the use of such a complex indicator, multi-indicator approach, we are able to characterize comfort more properly, and we are using actually the indoor overheating degree and the maximum heat index and the thermal autonomy index and the maximum operative temperature index. By that, we are making sure that we are not only estimating or evaluating the temperature or the air temperature in the building, but also we are taking into account the surface temperature. We are taking into account time, because these are not measurements that are done in a specific time step. They are done for the whole year. And then I can have a big picture or a realistic picture of what is the comfort condition in the building. So this is the second indicator that will be a key indicator if we want to assess and evaluate any building under the claim that this is a sustainable building or a green building that is providing shelter and providing quality for occupants. So now allow me to move to the second part of today's presentation, which is why whole life carbon buildings. And this is an important aspect. Just let me check if we can on the microphone. Somebody turn his microphone off. Yeah, we can go. So there's 2 important points when we are talking about whole life carbon. Historically, when we look at the building's life, we have to see that building can live up to 1,000 years, 800 years. It depends. For sure, in a country like United States, the life of a building is very short. In the United States, they can demolish buildings after 20 years or even after 30 years, 15 years. So they have a very short life. In India, for example, you are using a lot of robust materials, so the buildings stay for longer, unless the buildings are, let's say, in informal or less kind of sensitive areas. So we can see that there is a long a process of the life cycle of a building. And historically, we always start with the section that we are always missing, which is the emissions associated not only with the use stage, because most of the time we are only focused on the usage stage, which is the operational stage when the building is occupied and people are using energy or electricity for cooling or for heating, for ventilation, for electrification in general. But actually, we should not forget that there is a larger part that also we neglect, which could be responsible for around 18 or 20% of the greenhouse gas emissions. This part in red is associated with the construction stage. So the manufacturing of material, the mining, the assembly of the construction materials. This stage also is very important because it's associated with greenhouse gas emissions. So it's very important when we start to think about these emissions that we try to replace old construction materials that are like concrete, cement, which are very carbon intensive and polluting in their production, with bio-based materials. This is today the tendency in Europe. I hope it becomes a structural tendency, not just a cyclic short-term tendency. And as you can see, we are looking at the sourcing of these materials, the prefabrication of these materials in workshops to have a lean approach in the production. And then we make sure that even after the operation stage is finished, we can recover these materials by dismantling and disconnecting all the building connections and making sure that there is a kind of circular use and making sure that these material will not end up in landfills. And this includes also the renovation efforts for existing buildings. So this not new, I would say, this new focus, actually, we are more now focused on the embodied carbon emissions in buildings. This is very important to take into account next to the operational emissions. Now, I want to introduce you to the ISO 14040. This is a very important international standard, and all architects must be aware about this standard. And as you can see, the standard is divided into sections. The first section of the standard is the product stage. In the product stage, you can see that we are talking about all the activities or all the carbon emissions or greenhouse gas emissions associated with the extraction of raw materials, the transport, the factory, the manufacturing. All this is part of the equation. And then we have the section A4 and A5, which is more about the transportation to the site and the mounting or the construction of the building. And then we end up the first stage, which is called stage A, and then we can move in the green color stage B. Stage B is mainly related to the use, and here we are talking about the usage of the building, whether it's related to the energy use, which we can transform later on into carbon emissions. And this happens during the life of the building, whether it's 60 years, 120 years, up to 1,000 years. It depends on the function. And finally, we move on to the third stage, which is the end of life. And in the end of life, we are talking if the building is going to have some demolishing, any haul away waste material, if there is any recycling, disposal, and finally we can move to the last part of building's life, which is section D, which is beyond life cycle. Here, if we are going to really reuse any building material or recover it through elements or products that could be reused in future buildings. This ISO is so important because it implicates certain terminology. We need to know about the term cradle to gate, and here we are talking about building materials and building products that are used from cradle to gate. Then we have building materials that are related to cradle to site. Then we have the cradle to handover, cradle to end of use, and cradle to grave, assuming that the building material will be landfilled or incinerated. And then finally, what we are seeking is to have the cradle to cradle approach, so that we design buildings from the beginning like Lego or like units that could be disassembled and reassembled. It requires a lot of standardization, and it requires that we stay away from chemically connected buildings like concrete buildings or buildings that are not allowing to be dismantled. So this is the framework that is used worldwide, And every architect, when they are calculating their emissions of their building, one of the most important points when they are coming into discussion, we need to make sure we are talking about which module. If you are talking about your emissions of your buildings, the common aspect everybody is going to talk about is module B6. B6 means that we are talking about the carbon emissions associated with the energy use stage. But if we are talking about embodied carbon, then we are talking about A1, A2, A3, and sometimes also we can take into account the mounting and transportation. So you need to be accurate and precise when somebody is asking you about your carbon footprint of your building or the greenhouse gas emissions associated with your building in square meter per year. Every time you are communicating this value, you need to make sure that you are also associating this value with the modules that this value is corresponding to. So this is very important to take into account. Now, why do we need to have a whole life cycle carbon assessment? Because we need to have a comprehensive carbon footprint assessment. This will give us a full idea about the impact of our construction industry. We need to have long-term sustainability goals. Europe is trying to reach climate neutrality by 2050. Europe is trying to be a climate neutral continent, meaning that all buildings are climate neutral. China, for example, is doing it for 2060. I'm very curious about the Indian targets. I'm sure you must have something. It seeks also regulatory efficiency, resources efficiency, and this means that we are going to have a market transformation. We need to accelerate the adoption of green technology, bioclimatic design principles, and for sure we need to have a holistic environmental impact approach that thinks about circular economy rather on the linear economy that is based on production of waste. So these are the reasons why whole life cycle carbon is becoming today the most important objective for the building construction industry and architectural industry. As you can see, embodied emissions, operational emissions, and end-of-life emissions, those are the three terms we are using. And when somebody is operating or communicating, first thing we ask them, what are the emissions associated with the operational stage? What are the emissions associated with the embodied stage? And what are the emissions associated with the end-of-life stage? For sure, there is a negative emission stage if you have bio-based materials, because then we will assume that wood, timber, or any bio-based material, it's already storing carbon, so it has a negative emission embedded in the materials. So let's go for the following survey, and I would like to ask you to check this survey here. I will just open the survey. Let me answer is answer number 1. The stage that has the most embodied carbon emissions, or which stage of the building material life cycle contributes most to the embodied carbon emissions, actually is the extraction and the production stage. By carbon, we understand why it's important, what's happening with climate change, what are the gases associated with this phenomena, and why we are trying to reduce it. Let me now to open up a window for you for what's happening in Europe. Actually, Europe is trying to reach the target of carbon neutrality by 2050, and they are trying to do it in all sectors. They're doing in the agriculture sector, in the industry sector, in the construction sector. And this means if we are reflecting on the construction sector, all buildings must be full electric, because this means we will abandon the use of any fossil fuel. Maybe this is self-speaking in India, but you need to understand that Europe is, most of the cities are on a latitude higher than 40. And if the latitude is higher than 40, it means that they are heating dominated. So historically, Europe was burning coal, wood, biomass, fossil fuel in order to heat buildings. And in order to transform towards electric, this is a big transformation. And this will happen through heat pumps, using also low carbon buildings, decarbonization of heating and cooling. This is very important in Europe. The decarbonization of the energy mix. So historically, most energy mixes in Europe were based on coal and petrol. Today, they are moving away from those sources of heat and energy because they are polluting, and they are replacing them or compensating with either nuclear energy or with a renewable energy. But for sure, the focus is more on renewable energy. Nuclear is just seen as a kind of transition to stabilize the grids. And for sure, we are looking to low carbon building services. And you can see this is a milestone or a kind of a roadmap with the different milestones that Europe is expecting to have in order to move on. And by 2030, all newly constructed buildings must be zero carbon buildings. Now, if I take you further into the countries that are really advanced and they are changing their regulation and requirement for building construction, the most advanced country is Denmark, followed by France. And you can see that they have already regulation implemented since 2023 and 2022, and they are requiring a maximum threshold of emissions in kilograms CO2 per square meter per year for the whole life cycle of the building, which means that this value of 7.1 kilograms CO2, it is based on calculating the emissions associated with the building material inventory and associated with the annual energy or annual operation of the building and the emissions associated with this operation, including the end of life. This means that in order to get a permit for construction today in Denmark or in France, you need to have your building design ready, quantify all materials, quantify the greenhouse gas emissions associated with those materials, which means that you need to perform a life cycle assessment. Then you will need to perform a building performance simulation to estimate the operational emissions of those buildings annually. And you will add up the embodied emissions with the operational emissions, with the end of life scenario, expecting what happens after the life was demolished or stopped being used. And you add up all that, and the threshold should be under 7.1 kilogram CO2 equivalents per square meter per year. So this is the first time in history that we have building regulations that does rely on this factor of emissions. So it's very important to take this into account and to prepare ourselves to cater for those markets and to be able to provide services, because this means that new constructions in these countries are mainly timber buildings, bio-based material buildings. As you see here, this means that for the first time we are seeing countries that are not only anymore standing and focusing on the operational emissions, but they're also looking at the embodied emissions and the end of life. And this means that this way of thinking is changing the way of designing building. And for the first time of history, we are looking at materials and energy in the same time, not only energy. And you can see that there are already softwares and applications that allows you, while you are designing the building, to directly give you an assessment. You can see down in the colors green or red if your building design is close to the requirement of the code or far away from the requirement of the code. And you can see this means that you need even to choose material, and I can promise you already this means that the use of concrete is done. We cannot anymore use concrete. We cannot reuse easily reinforced concrete. We're talking here about bio-based materials. Concrete and steel will maybe only used in the foundation or maybe in the shafts for services, or the batteries of the building for security, for toilets and for staircases, for the lifts. But the rest of the building, the slabs, the facade, the roof, everything is made of bio-based material, whether it's bamboo, timber, hemp, whatever is available in the country. And by that, we can see that the greenhouse gas emission intensity is going to a lower side. So this is also matching very well the ESG strategies, which are part of the environmental social emission calculation approach, which is also required by all companies. I don't know if you are aware about Scope 1, Scope 2, and Scope 3. Any corporate company or the whole business world is now obliged to report their emissions based on Scope 1, 2, and 3. And here's tenants, meaning that tenants are starting to look and demanding for low carbon spaces. This is on the market. We can see it in the real estate market. Office buildings reflect corporate carbon commitment. And the market is now seeing more rents higher for spaces that have low carbon emission. And all companies are obliged to calculate their indirect and direct emissions associated with their economical activity, which bring us closer to be able to calculate the carbon footprint of people. because in order to be able to calculate your carbon footprint, you need to know what are the emissions of the buildings you are living in or working in, and you need to have the emissions associated with your mobility or your transport mode of transport, and you need also to have the emissions associated with the food that you are eating. If we combine all this information, we will be able to estimate the carbon footprint per citizen or per person. And from there, we can start to have some budget in order to say, okay, if a country wants to respect a certain threshold of emissions on a national level, what will be the budget per citizen? And just to let you know, today in Europe, if you take the airplane more than one time per year, you will be taxed with a carbon tax. So these kind of approaches are coming closer and closer. And this means that we as architects and designers, we need to be very good with understanding what are the building materials that are available in the market and what are the emissions associated with them. And I invite you all to check this material pyramid developed by the Denmark, as you can see down in the website. And you can see the top high emission material is aluminium, steel, and then it's more the inert or density material like concrete, fired brick, and then you go down until you reach to bio-based materials. So today it's very important to understand that the most emitting material is reinforced concrete, red brick, clay brick, concrete, and so on until we go down to bio-based materials. And if we want to have a low carbon building, we need to dwell in the knowledge of low carbon materials and start to use low emission materials. And I always use this checklist when I do projects with the key answer, and I try to answer them about does the material fit the purpose, to what extent is your material available, and so on. So I advise you to use this list of 10 questions to make you familiar with the use of materials. What do we have here also in general? Embodied greenhouse gas emissions. This gives us a broader view on the carbon, whole life carbon. And today we are doing a breakdown, complete breakdown for facades in order to get an idea about the emissions associated, even with the shading devices, with the glazing, and so on. And this means that on the total, for the flooring, for the partitions, for the opening, for the windows, insulation, cladding, walls, and floors, you will have always an estimation of the emissions, and you might have a budget in kilogram CO2 equivalent per square meter. This means that when you're starting to take your decision, you start to always select materials that have lower environmental impact. And this means that most probably we end up using materials like timber, straw, cork, hemp, bamboo, depending on the region you are located in. And this means that we also will try to use materials that are trapping or storing carbon, like biochar. Today there's a lot of trials to produce concrete with biochar or with captured carbon, or to have biomineralized materials with low carbon aggregates that are mixed in the concrete mix to make sure that we have low carbon concrete mixes. We are also using environmental product declarations. So these are kind of declarations that are already based on a life cycle assessment for building products. And it is now obligatory in Europe for any building material to be available on the European market, whether it's imported or fabricated in Europe, that it needs to have a certificate which is called environmental product declaration. And as you can see, this environmental declaration is reporting on the global warming potential in kilogram per unit of the building material. It could be per kilogram, per square meter, per cubic meter. It's reporting on the ozone depletion potential, the acidification potential, the eutrophication potential, the photochemical ozone creation associated with the material production, the abiotic depletion potential also are part of these reported data, so that any architect or any designer can directly estimate the quantity of material, multiply the quantity with those emissions or these aspects related to depending on the criteria you're focusing on, and then you can quantify this impact. I will move on because we are a bit late with time, but this means that what we are now facing in the architectural engineering and construction industry, that for the first time in history, we are trying to bridge the gap between the embodied energy and emissions from one side, and on the other side, the operational emissions. Historically, this was never done. Historically, we were only doing building performance simulations to estimate the operational emissions, but today we are forced to do life cycle assessment or life cycle impact assessments next to the building performance simulations so that we are able to figure out what are the emissions associated with the embodied or with the manufacturer or the construction of the building and the emissions associated with the operation of buildings. And then we add up both emissions to have an idea what are the emission intensity of buildings. This means that we are looking for low carbon solutions. We must focus more on renovation. We must focus on design with flexibility, design for disassembly, the reuse of existing materials. And this is part of the challenge for sure. And we need to use industry byproducts instead of cement, use recycled concrete, reduce the concrete in general, like I said, only making it available or used in foundations or in the core of the building. And for sure, we need to use more and more timber structures like CLT, cross-laminated timber, for example, and use hybrid systems, timber and concrete, because for fire safety, it's important. For acoustics, it's important to keep using still concrete materials and make as much as possible our timber roof elements made of standard structure, and for sure maximize the use of bio-based materials. As you can see here in Europe, there is a lot of massive insulation initiatives. Buildings in Europe are mainly heated most of the year and they are not insulated. So here you can see full renovation initiatives where we can come up in 7 days or 6 days, renovate a complete building and make sure that we are using low carbon materials, and the facade after can reduce the emissions associated with heating up to 80 or 90% because the building will have a good envelope. It does not need any more constant use of petrol or gas, natural gas for heating. And by that, we can reach this carbon neutrality. This is just an example for what's happening on the ground. Another aspect that we can see, I know many people in India will laugh about these slides because in India, you are building high density and you have a high population, you have a shortage of housing, so you cannot build like the Dutch. This is what the Dutch are building in 2024. They are using these kind of timber low-rise developments, fully covered with photovoltaics. They have a solar thermal panel for domestic hot water. They are using a heat pump. All building materials are bio-based. Insulation materials are cellulose. And you can see that almost there is no concrete, only in the foundation, kind of slab. The rest of the building is low carbon. And these are the kind of examples of zero carbon buildings, fully made of wood, local wood, or wood coming from Central Europe. But for sure, I understand that this is a low-rise development, but I would say we need to move step by step. Maybe in Europe, we can build up low-rise, but with time, Europe also has areas and cities that requires to have mid-rise and high-rise. And I'm sure that we will reach we will succeed in this challenge and we'll have high-rise timber buildings soon, even though we have a lot of issues related to fire and acoustics. And here is an example I wanted to share with you. This is a building designed by Arup. It's in Amsterdam. And it's one of the few buildings that reached, I don't remember how many floors, but something around 15 or 20 floors. So the building in the middle here is a timber building. For sure, there's a lot of glazing. This would be too much for India regarding overheating. But we are talking here about Amsterdam, which is on a latitude of 54. So it's a cold climate. So it's still tolerable with passive heating. But the whole building is made of timber. So it's very important to take into account. And it is using sprinkler system. So the building has a centralized sprinkler system in case of fire to kind of avoid any risk of fire. So this is an example for such work. Now, I just want to have your opinion if you agree to have one last poll with me before wrapping up. Can you answer this poll? I would invite you to have a look at this. Do you think we can build high-rise buildings in India using timber or bio-based materials instead of reinforced concrete? Important that we listen to everybody and engage maybe in the Q&A after to justify the yes and the why behind it. Okay, so I need to wrap up because of the time is running. So thank you for those who answered. Now, just very fast, I will go through some solutions, some ideas. What should we do if we are now aware about the greenhouse gas emission phenomena and what happens with it, why it's happening, what do we need to do? By default, zero net carbon buildings, they appear as the only way to make it. And here we are talking about grid connected buildings. And for sure, you need to apply the bioclimatic design principles and the energy efficiency principles and never underestimate the indoor environmental quality. And therefore, I mentioned that we must use complex overheating or comfort indicators associated with emissions, because before making sure that we are building low carbon buildings, we need to make sure that those buildings are comfortable and they are allowing people to survive. And in India, it's becoming very serious, the problem of overheating or discomfort. And there is no chance to not design buildings that are allowing people to live and save their life during extreme heat waves that are very long, and even during power outages, assuming also that there is a big part of the Indian population that is unable to afford air conditioners or even have access to electricity. So there is no chance to abandon those people. So therefore, no talk about zero net carbon buildings without talking about comfort and indoor environmental quality. After that, we can introduce the idea of HVAC systems, having cooling or heating systems. Storage is very important. We can have plug-in batteries, and finally renewables. Those are the foundations or the basis if somebody wants to design a zero net carbon building. And you can see today in Europe, most of the buildings are using a heat pump and using photovoltaics that are coupled. The envelope is well insulated. We have a little surface of glazing. Maximum 30% of the surface is glazed. So the window to wall ratio is maximum 30% to avoid overheating risk during the summer. And we are introducing floor heating or floor cooling in the ground floor or in the sleeping areas. And what we are doing today, the energy mix of Belgium, for example, is nuclear. But on the long term, we are phasing out of nuclear and introducing renewable energies. And this will take time before we will be able to make the renewable energy mix dominant in our energy mix. If somebody tells me, okay, what about the United States? Same story. United States, they have a very nice standard, which is ASHRAE standard 189. And in this standard, they're also looking at the electrification and the decarbonization of buildings. They're focusing on improving efficiency, improving the electricity or electrifying everything, and phasing out completely fossil fuel, even for cooking. And this is also a challenge here. This means that already in the Netherlands, it's not allowed to cook with using natural gas. Imagine that the Dutch, since 2018, they're only using electricity for cooking. This will even change your habit in your cuisine or in your kitchen. And it's very important to start to be ready and prepare future buildings for these challenges from now on. It will be also a challenge always to mix and balance renewable energy with energy efficiency. Some climates are heating dominated, some climates are cooling dominated, some climates are mixed use. They need cooling and they need heating. So it will be very important to answer these questions, and building energy simulations will help you to estimate the energy demand, the cooling demand, the heating demand. And therefore, when you will introduce your bioclimatic design strategies, you need to be first understanding what are the dominant demands of the building so that you introduce the proper, appropriate design strategies. Also, what we are realizing in the last years that we are not anymore using high temperature heating. We are only using low temperature heating because building envelope are well insulated and they are airtight. So we need very low temperature for heating in Europe, and the same story applies for cooling. If we have a good envelope that is insulated and it's airtight, and we don't have a large glazing surface, we have external solar protection, our need for cooling can be very little even during extreme climate conditions. So the tendency worldwide is to use heat pumps and to make sure that the buildings envelopes are high performance. And even we can see in countries like Finland that they are using large-scale heat pumps that are serving full neighborhoods. So here we are talking about a full heat pump that is serving 30,000 homes. This means that there's more investment in district cooling and district heating. And this could be also a potential in the future. I don't want to go here in detail. I will go fast, but there is a big potential for district heating and district cooling. It requires to have a strong central governance. It requires to have also a strong local governance. It's not available in many countries. But this is also another approach to make sure that we introduce these kind of neutral grids and have centralized heat pumps for cooling and heating. And like I mentioned earlier, we are on one side decarbonizing our buildings, and in the same time, we are trying to make them more resilient, because while we are doing that, we have a lot of shocks and disruptions. And this means that we need to invest a lot in storage. Storage could be in the form of thermal mass. We can have technological batteries. We can have thermally activated beams, phase change materials. We can use buffer tanks, floor cooling, floor heating, or we can apply this storage technology on the large scale, on the urban scale. We can use micro hydropower, energy storage system, geothermal system. Allow me also to share with you these technologies that are penetrating in the market in Europe. A lot of these plug-in batteries, they are not very expensive in the European context. They cost something around 500 euros. Many households are plugging them, but I'm talking here about households that already installed minimum 15 to 20 square meter of photovoltaic while they are using these batteries, because they are making sure that they are storing the energy during the peak production when everybody is producing and nobody is interested in importing energy. And then this allows them to shave the peak of production and also extend the night use of energy without relying on the grid. So this will be also kind of technologies. Maybe in the global south, we are more used to use these kind of batteries because we have power outages. But it's interesting in the West that they are also using them now to kind of balance the energy export-import balance. And for sure, phasing out of refrigerants that are polluting is also very important, because we will need more and more cooling under a climate that is getting heated, a planet that is heating. And this means that all the refrigerants need to be friendly, and we need to phase out the polluting refrigerant that includes chlorofluorocarbon or hydrochlorofluorocarbons by more friendly refrigerants that are more modern, and make sure that we are avoiding the leakages. These are some equations to calculate the emissions generated by refrigerant leakage, because this should be part of any carbon operational carbon emission calculation. But I will leave the slides for you if somebody can explore them. And as you can see, I wanted to share with you also that in Europe, there is a rolling out of smart meters. So smart meters are very useful, because then we can couple internet with energy. And this means that occupants, they have an idea about the emissions of their energy or electricity use. And based on that, they change their behavior. So if you are during midday, you can have an idea, okay, my building now is emitting electricity or using electricity. And you can see here that this is Belgium. In some moments of the year, this is a plan for the whole year. Actually, the emissions are negative, because we have so much renewable energy pumped in the energy mix or in the grid, that this is the best way to start use electricity, because it has a negative impact. While we have other areas of the year that we have negative emission impacts. This means that occupants can know now every 15 minutes what is the emission intensity of the grid, and based on that, they decide whether they are going to iron their shirts, or they turn on the washing machine, or they turn on the heater or not. And this is also another important aspect coming up in the future. Well, I will move on further to wrap up the presentation, because we are running out of time. Well, some concluding remarks. The transition towards zero emission buildings is moving from the energy, or the nearly zero energy or net zero energy, towards zero emissions. This is a concept that we are moving from the trias energetica to the trias materia, meaning that It's not only now energy that we are working with, but it's also materials. And we are all seeking to reach zero emission built environment. We should keep it in mind on the level of cities, on the city of neighborhoods, on the level of buildings. We developed in our lab a framework for calculation and modeling of carbon emissions of buildings. It's open access, so I invite you to check it. You will find on YouTube videos also that we are explaining this framework. Any person who is interested to calculate the emissions of a building, how to do it methodologically in a scientific way and in the same time professional way for companies. So this is my gift to you if you are interested. But some concluding remarks that are very important. What should we do and what should we remember of this presentation? Well, I advise you to adopt the new indicators of global warming potential and make sure that you address module A, B, C when you're talking about zero carbon emission buildings. Get experienced with carbon numbers through the environmental product declaration. Try to get familiar with the top mostly used materials in your projects and look or fetch for environmental product declarations to understand, okay, 1 kilogram of this material is equivalent of how many kilogram of greenhouse gas emissions, so that you have an idea how much polluting is this material. Use consistent methodologies and software for life cycle assessment. For example, one-click LCA, Design Builder, IES Virtual Environment. Those are very good software. I recommend them to use them. And make sure that in your design, as if you are cooking, for the ingredients of your building, reduce the building area, minimize the car parking, use high performance building envelope, use electric heating and cooling, use biogenic materials, make sure that you are under the 40% window to wall ratio threshold, use plug-in batteries, use solar photovoltaic and roof on the roofs and on the facades, especially south, west or east. And for sure, some directions begin by setting a decarbonization performance goal and limit these emissions for your project, and start by mixing the smallest building area with the minimal parking. Next, add a high performance building envelope alongside an electric heating and cooling system, and add a pinch of photovoltaic and a large scoop of biogenic materials, and run the energy and life cycle impact assessment simulation to make sure that you have an idea about the energy or the emission intensity of the building. Well, this is the end of my presentation, and I'm available for questions. Thank you very much.
Thank you very much, sir, for an excellent presentation. Participants, I would request you to please unmute and ask questions. If you have audio issues, you can type your questions in the chat box as well. So I want to ask a question.
Yes, go on.
In India, actually, it's a tropical country, and summers actually occur in every part of the country, once in a year. And the green cover is usually less. It's gradually becoming less, and we see a lot of images, that shows the green cover is becoming lesser and lesser from the previous time. So we don't feel that timber is a suitable material, because still we are in a state where we are trying to plant more, and we are, going towards afforestation right now. We don't cut wood or a tree for timber for construction. So in that sense, what will be the suitable material in India? Like you said, use timber in your construction, but we are not able to, kind of relate with it, because we know the scenario what it is. Everyone who is present here, I think they are all, talking on the same lines. But what will be the suitable materials, if not timber, in Indian
Yes.
context?
Thank you for the question, and the question is completely, I agree with you, it's relevant. And let's go to the basics. The basics is that timber, when I propose timber, it's a more, I'm talking about a solution, but we shouldn't be busy with solution. We should be always busy with the principle. The principle is to use local materials that are abundant and that are of low carbon impact. If we try to ask ourselves the question of what is available in India as a low carbon material in abundance without competing with forest, with vegetation, then maybe we find agricultural waste, maybe we find industrialization of agricultural waste and biomass, and the use of low technology or low tech construction techniques that make sure that the carbon is low, meaning that we might end up using clay or earth or earth-based constructions, but we make sure that we don't use cement, or we protect it from the cement component, or we can use agricultural waste like rice. Rice produce a lot of waste. If we can industrialize the agricultural sector waste, sugarcane, rice husk, wheat. I think India is full of bio-based material that is considered sometimes as waste and incinerated. If we can stream this waste into the construction industry, then we are not competing with other resources like timber. And for sure, India, like I come from Egypt. In Egypt, timber is more expensive than gold. Do you know that? It's so expensive because we don't have forest, we don't have trees, we don't have water. You are in the desert climate. So timber is like gold. So it doesn't make sense to use it at all. But still, I would say we try to give chance for the engineers and the professional architects and for material scientists to figure out what could we do. And we shouldn't be harsh on ourselves. We just take time. But we must know that it's not anymore possible to continue building with reinforced concrete and pour it all over the places. Even if we use it rationally and allow for innovations to figure out and answer this question. So thank you very much. It's a very good remark. Thank you.
For the answer, yeah, a lot of things we can do. Still, a lot of research is going on the bio waste and biomaterials right now. There is another question in the chat box. Hi, an alternative to reduce embodied energy in India is alternatively use load-bearing construction instead of RCC frame construction, especially for low-rise and medium-rise buildings. Can you share your thoughts on this, please? And this is asking this question.
So just a sec. The question is in the chat box.
Yes, yes.
Which one? Can you just point to the name? Alternative. Yeah, the load-bearing construction.
Yes, yes.
Yes,
The
I
second
think.
one.
Yeah, I think also we failed in the global south, because I can talk in the name of the global south. I work a lot in countries in the global south. I originally come from Egypt, and I'm still visiting also Egypt a lot. I think we failed to build low-rise and mid-rise buildings without using concrete. Actually, we are putting concrete in everything, while we don't need to use concrete in low-rise and mid-rise. I think even up to 6 floors, we can go without concrete if we do well load-bearing. But the problem is that under the westernization and the influence of the colonization and the Western lobbying of cement industry, or our building codes do not allow for the use of bearing walls structures. So if you see the Indian code, the Egyptian code, Africa, and so on, it seems that as if the only way to build even a single floor building, we must have reinforced concrete columns, and we must have recast concrete. So I think to unlock this challenge, we need to update our building codes and allow for alternative structural methods and construction technologies. Only, I'm not talking for high rise, I'm talking about low rise construction and mid rise, that encourage the use of the bearing wall techniques or load bearing techniques. And by that, we can have full construction without concrete, and they can be low carbon. And I think this could be also interesting approach to encourage young architects and designers to ask them, can you build a 6-floor residential complex or buildings without concrete using traditional safe construction? And for sure, they can be also earthquake resistant, because I study a lot structure. I know there is no problem with safety at all. And even if we will use the concrete, it will be only used in the slabs, in the floors, because we cannot completely avoid it. It will be only in the floors, but then I can reduce the quantity of concrete by 50%, by 60%, and only use it in essential area. And then I can reduce the global embodied emissions of a building by up to 75% just by through design. So it's important to find these standards and codes and work on allowing for alternative paths in the national code rather than just think about the skeleton post and column concrete structure that is going in all buildings. Good question. Thank you very much.
Yeah, Anirudh has raised a hand. You can please ask them.
Yeah.
Okay.
Yeah. So it was a follow-up question to that question about the load bearing that I just asked. Thank you so much for your response. So, as I'm a practicing architect, and essentially what I mainly practice in is load-bearing construction in India. We mostly do mid-rise and low-rise building. One of the load-bearing buildings that I've done is a 5-story structure, in fact. So we've used a mixture of what we call as stabilized mud blocks, which is these compressed stabilized earthen blocks, and as well as stone masonry to create essentially unreinforced pillars using stone in points where there are higher loads. So one of the ways we have also tried to reduce the overall embodied energy is to also alternatively use alternative kind of roofings, where we have now started doing masonry roofs as well, like domes and vaults. We are doing it, in fact, even in the intermediate floors, not only in the end floor where we try to make a shallow dome or a shallow roof, and then make it flat on top and build another floor on top. So these kind of practices is quite common in India since quite a lot, since quite some time. So I feel these are one of the practices that would, as you were mentioning, it's a low-tech practice, right? Because this skill is readily available in India to do this kind of work, and it does not require a lot of technical training needed to be given to the people who do this work as well.
Thank you for your input. I fully agree with you, and I salute you for mentioning the stabilized mud blocks and the use of stone, the use of alternative roofing. But this means that we need to have our innovative part of our profession, bring it more forward. And I would say that if the regulation is adopting the greenhouse gas emissions indicators, you will figure out that even in public tenders and in competitions, automatically those solutions will be selected. Because today, maybe you are doing that from a good heart or from a good environmental, let's say, awareness, but you are not rewarded for that. But once we are having an indicator of global or greenhouse gas emissions of kilogram CO2 per square meter, and it's becoming part of the Indian regulation, and decision makers are not only focused on the cost, for example, but they are also looking at a reduced emission per square meter of built-up area next to the overheating risk or the thermal autonomy criteria, because this is so important also to make sure that the buildings are thermally autonomous and they do not rely strongly on cooling systems or active systems, or at least they will provide proper comfort conditions. Automatically, these solutions of low-tech construction techniques, they will be rewarded and the projects will be selected. And we need also to bring that to the regulation to make these solutions automatically part of any best practice. Thank you
Yes,
for
sir.
your
Yeah.
input.
Thank you, Anirudh, for sharing your practice. There is another question from Lagnita. Are you also exploring on new materials at the D phases that could be recycled or may even used as a fertilizer?
Yes, well, I am an architect and a scientist in the same time, and I work in different areas. So one of the areas is material science. So because we need to master a lot of things. We need to know about structure. We need to know about material. We need to know about sustainability and the environmental impact. And I'm a bit I'm a bit frustrated with the material science people because unfortunately, many research that is conducted on new materials or innovative material, we focus more on the mechanical properties or the chemical properties like the thermal resistance or the mechanical resistance or the physical resistance, and very little studies focus on the environmental impact. So if you know about the different construction technologies, for example, I don't know, in India, do you have okra? Okra, that's okra that we eat. Is it called okra?
Yeah, here we call it lady's finger.
Lady fingers, voila. Here you go. Lady finger, in many situations, they are they are not used anymore for food. Sometimes they are getting too old or drought is hitting them. They are very fibrous materials. And we are working in Burkina Faso in Africa with a project to break them down and add them to compressed earth blocks as fiber to compensate for the compressive or the tensile strengths. So there is a lot of innovation, and I think we will continue innovating, and I think we can have hundreds of new products, mixing waste, bio waste, whatever kind of fibrous material with earth construction. But what I'm regretting here is that we do not perform environmental impact assessment for these materials. We do not quantify how much they are less intensive regarding the carbon emissions compared to the cinder block or the concrete block. So it's so important that whatever endeavor of creating or innovating with new construction materials, we must always use an environmental indicator so that we are not only focused on the physical properties and the compressive strengths and all the structural properties, but we need also to quantify so that I can tell if I'm using a brick-fired block, how much carbon is associated with this, and if I'm using my innovative material, how much carbon emissions are associated with this new material, so that we can quantify it. And unfortunately, in many compressed earth blocks, for example, materials or earth-based materials, people introduce cement. And once you introduce cement as a stabilizer, up to 5%, 8%, the environmental impact of this new innovative block is equal to the cinder block or to the concrete block. So it's very important that we keep this into mind, that we associate all endeavors of innovating and creating new materials with quantifying their environmental impact, so that you make sure that they are really low carbon and they will not compete with already polluting products that are on the market. Long answer, but yeah, it's a very good question also. Thank you.
Yeah, so thank you for the answer. And same, same person is asking another question. In India, energy mix is mostly non-renewable sources, maximum percentage. With that, how could we improve on development on terms of material, production and usage? And how could we do better in terms of construction as a whole?
Thank you for the question. It's a difficult question for sure, because India is relying too much on coal in the energy mix. So you have a very high emission factor. But still, I would say I will not blame India because you are still have the right to develop, and we cannot come with a condescending approach from the West saying, no, you have now to use low carbon, invest in nuclear or something. What I would say is that I think in general, we should just more and more invest in renewable energy. If we can have photovoltaic systems more and more on the building level, on the even farming level, today there is a lot of solar farms in many countries that deliver more revenue than farming a crop. For sure, this could be competing with food. We don't want, for example, India was not allowing to export wheat or rice some years ago because you wanted to have a national security from a food point of view. So it's a complex thing. I cannot advise easily, but I would say, I give you a very funny example. Do you know that there is a sustainable company in Austria? They produce their beer, only during May, June, and July, August, and they produce the whole stock of beer from renewable energy. So they created a factory, and the factory is only operational 4 months of the year when the solar energy in its peak. And then they create the whole stock of beer, and then they close the factory. No more production. And they just manage the stock over the 12 months periods of sales. And sometimes in February or in March, the beer is finished. And clients keep asking for buying more beer, but then the company says, sorry, my stock is finished. So here, this is an example of an industry that intensified its production during the peak production period of the solar energy, because in Europe, we don't have monsoon. In Europe, we have very bad climate all the year, but then only in the May until September, the sun is shining and we have open skies, and the photovoltaic production is very optimal. So I would say if we can see in any region what is the renewable resource of energy, whether it's hydropower, whether it's renewable solar electric, whether it's solar thermal, whether it's geothermal, whatever renewable source of energy, and we intensify the production of building materials during those periods of peak production, maybe this could be one of the alternative solutions. For sure, producing beer is not like producing building materials, but I'm just trying to share with you and brainstorm. I don't have an answer for that. Thank you very much for the question.
It was a very nice example, which talks about self-sustainability, which is very important. So even in India, some of the building material industry can work on the similar models in order to satisfy a demand for a particular season. But in India also, construction season is there because of the rains and other seasonal shifts. So it can work on certain models. Thank you very much for sharing that. Anybody else has any questions? You can unmute and ask your question. Thank you, Professor Atya, for sharing sharing the presentation. It was very, very informative. And on behalf of Council of Architecture, India, and SBB School of Architecture and Planning, I extend my deepest gratitude for you for this enlightening session, covering the comprehensive range of topics. Your insights into cause of climate change, both globally and within Indian context, and the discussion on carbon neutral communities has provided a crucial understanding on the present challenge we are facing right in today's time, and also the emphasis on the net zero carbon building and importance of addressing whole life carbon impact, including the embodied and operational emissions was both timely and very impactful. Your exploration on net zero whole life carbon buildings highlighting strategies and a corporate ESG strategy gave us an actionable framework for achieving sustainability. So very good takeaway was that. Also the pyramid of material that you showed was very, very informative. Additionally, our examples of decarbonization pathways ranging from energy efficient heating and cooling, district systems, all electric solutions with heat pumps, smart energy grids, demonstrated very practical and scalable solutions for transitioning to zero emission building projects. So thank you for your time, sir, and your expertise towards a more sustainable tomorrow. I'm very sure you are already contributing. You will be more contributing to this team. And thank you very much for sharing all your knowledge technology. Thank you very much. We look forward to implementing valuable insights what we have shared today into our academic and practical. Thank you very much.
Thank you for the invitation, everyone, and feel free to explore and share the slides with everyone so that people may benefit from it. And thanks for your patience. Good luck with your works and your projects. Thank you. Bye-bye.
Thank you, sir. Okay, participants, please take a 15-minute break and all of you please be back by 12:35. Our second session for the day will start at 12:30 sharp, but please be back by 12:35. Thank you very much.